In this video, we're going to talk about volumes and volumes of revolution. In this video, we're going to talk about volumes and volumes of revolution. As you can see in the video, there are many objects in the real world that can be described as volumes of revolution. Let's begin by thinking about how we can compute the volume of a sphere. We've been slicing, so you might think of taking the sphere and putting it through something like a bread slicer. If you do that, you're going to get discs that look very similar to these slices of oranges that I've put on the right. If you find the area of the circle and multiply by the thickness, you'll get the volume of one of the slices. Sum over all those slices, and you'll have the volume of the sphere. So let's look at how this works in practice. We can partition the interval from 0 to r into n equal slices, each of length delta x, which is r over n. So when we look at each of these, each of them is going to be like a slice of orange. And we look just to the right-hand side because if we double it, we'll get the volume of the whole thing. But let's look at this a different way. Suppose I slice and I just look at the kth region, the kth slice. If I take that slice and I rotate that about the x-axis, I'm going to get a little disc. It's going to have a little bit of thickness. It's going to be like this. Disc with a little bit of thickness, like one of those orange slices. And if I find its area, multiply by delta x to get the volume of this disc, and then sum these up, just in this top quarter circle, I'm going to get the volume of the sphere. Well, actually, of a hemisphere. And I'll double it to get the other side. So let's take a look at this. We can look at this by saying we can take this region, shaded in blue, and rotate it about the x-axis, and we'll get this disc. It's just the same thing that we had done above. But we could also take this same region and instead rotate it about the y-axis to get a cylinder, and we could build up the sphere that way as well. Again, we'd get only half the sphere, the northern hemisphere, let's say, and we would double that volume to get the other. The approach on the right amounts to slicing the sphere the way that you might slice an apple or a piece of bread. Whereas the way on the left really amounts to doing something like coring an apple, where you take successive cores that are bigger and bigger in radius. When you rotate a rectangle about a line either perpendicular or parallel to it, there are really only 3 different cases that you need to consider. Suppose, for instance, that we rotate this rectangle about a line perpendicular to it and right at its base. Then what we'll get is a disc with a little bit of thickness. Here's the disc. And we want to know its volume. So the volume of the disc is equal to the area. This is solid, right? So the volume is the area, or pi r squared, area of a circle, times delta x, the little bit of thickness. So this one looks like a coin, a disc or a coin. Now, in this next example, if we rotate this rectangle around that line, what we're going to get is a disc with a hole in it. So it's kind of like an annulus. It has a little bit of thickness, just like in our last case. It's got a little bit of thickness. And I'm going to call this an annulus or a washer or a bagel chip. Or if you eat your pineapple in cans, it's a pineapple slice. And its volume is, well, let me call this big radius capital R, and I'm going to call this little radius little r. So the volume is going to be the area of the big circle, pi big R squared, minus the area of the hole, pi little r squared, and that'll be the area of this annulus. And then we need to multiply by delta x, its thickness. Okay, and in this last example, we take the rectangle, rotate it around that way, and the shape that we're going to get is a hollow cylinder. With, again, a little bit of thickness, just a tad. And I'm going to call this a cylindrical shell. And basically, it looks like a piece of paper rolled up. So if we want to find its volume, well, just picture taking a scissors and cutting along the height and unrolling it. So the distance along the top, distance along here, is going to be 2 pi r. When you unroll it, it'll be the circumference of this circle. And we multiply by the height, and that's the piece of paper that we roll up to make the cylinder. And then it has a tiny bit of thickness, and that's delta x. So now I want to go back and see what all these letters and symbols mean in terms of the picture. So here, in this case, we need to say, what's r? What's the radius as I rotate? And r is going to be this distance. In the next example, I need big R. That's going to go from this top piece to the axis of rotation, big R. And I'll also need little r. And that's right here from the bottom to the axis of rotation. And in each of these, delta x is just that tiny little thickness, delta x. Here again, we have delta x. Okay, so what's r? R is the radius. Now, I'm going to draw that very deliberately right here. This is r. And h is the height of the rectangle. So that is h. Now, this one you have to be a tiny bit careful. This is r, so is this r, right? So is that r, And so is that R. But I wouldn't do any of the last two, because if you draw R way up here, you'll think it has something to do with the top of the rectangle. And it doesn't. So I wouldn't do that. And if you draw R down here, you'll think it has something to do with the bottom. So I draw R somewhere in the middle so that I know it has nothing to do with the top or the bottom of the rectangle, just the distance between the line and the rectangle. So doing these problems just amounts to being able to label distances and describe them. So for instance, let's go back to case 1. R is a vertical distance. Vertical distance is always the top y value minus the bottom y value. Any vertical distance, let's put this down here. A vertical distance will be top y value minus bottom y value. And that will give us this distance. How about a horizontal distance? So here, top y value minus the y value of the axis of rotation. Bottom y value on the rectangle minus the y value on the axis of rotation. Similarly, H, it's top y value minus bottom y value. What about R? R is a horizontal distance. When you're measuring a horizontal distance, you've got to take the big X value, large X, that's the one furthest to the right, minus the small X value. So it's rightmost minus leftmost. And as long as you can describe vertical and horizontal distances, you are set for life. So, what's the point here? The point is, if you have a volume that's a volume of revolution, you don't need to cut the actual 3D object. You could start with an area that you're going to revolve, chop that area, and just revolve the kth slice. If you can figure out which volume you get, it's going to be one of these 3 cases. For the kth slice, you just sum over all the slices and you are all set. So, there are a few things that people sometimes get confused about. Discs usually are solid. But what's the difference between an annulus and a cylindrical shell? For a cylindrical shell, the height of the shell is substantial. Whereas here, for an annulus, the height is simply delta x. For the cylindrical shell, the difference between the inner radius and the outer radius is negligible. The distance is just delta x. Whereas for an annulus, the difference between big R and little r is not delta x. It's larger. So try and draw them differently, and the main thing that you need to figure out is which of the 3 cases you're in. So you're going to be practicing this and seeing how that goes.